So this video tutorial is going to explain the effect of concentration on our cell EMF, meaning when we see E naught of the cell, what this is telling us is this is standard conditions, which imply 1 molarity of concentration for all of our solutions, as well as 1 atmosphere of pressure. Now, when you have standard values, you see this naught sign, you use this very simple equation where you find the E values for your oxidized substance, which is your anode, and your reduced substance, which is your cathode, and you simply take the difference between the cathode and the anode to get E naught of the cell. However, when you are operating under non-standard conditions, and therefore you have likely wavered from this 1 molar concentration, you cannot just use this simple equation to take the difference, because there is going to be some variation due to this difference in concentration in your E value of the cell. So how does concentration affect it? It will slightly increase or decrease your value, and by slightly we mean just maybe a tenth or a few tenths of a volt, but it is still going to be different. Therefore, when you are operating under non-standard conditions, you will therefore use the NERST equation in conjunction with your regular equation and find how much the E naught of the cell, the original standard value, changes. By what factor does it change when you're operating under non-standard conditions? So, how do we do that? We've got these two equations. Either one is okay to use. One uses the log of 10, one uses the natural log, and so either one will render the same response. It is just a personal preference of what you use. I'll be using this one. This is the one we see most often. Notice that we're using the E naught of the cell, and what this is telling us is that this is what would be under standard conditions. How much does it change? By this value right here. We're going to subtract whatever this number is from the standard value, and that should tell us what E of the cell is. Not E naught, E of the cell, based on the E naught minus this deviation. So, let's take a look. What is this N value? The N value stands for the number of electrons, just as it always has, and this 0.0257 volts is the constant up here that we have already calculated, so it's already part of the equation. So we've got our constant, we've got our number of electrons, and that only leads us to what is this Q, this ln of Q. This quotient is equal to something, right? And what is that? That is your ratio, the ratio of your oxidized substance concentration and your reduced substance's concentration. Again, it's not 1 molar, so it's got to be something. So once you determine what your cathode is, your reduced substance, that is the concentration that you will place here in the bottom of your equation, of your fraction. At the top, the numerator of your fraction will be the concentration of your oxidized substance. Take the ratio, the natural log of it, multiply by this value, and then take the whole product of that and subtract it from the E naught of the cell. So first you need to calculate E naught. You need your number of electrons, and you need to know the ln of your oxidized to reduced concentration, that ratio. So let's take a look at this example and see what it asks us to calculate. They would like to know what the potential of the cell is that is composed of zinc and copper at 25 degrees Celsius if the zinc concentration is 0.25 molar and the copper is 1.5 molar. So the first sign that this is going to use the NERST equation is that we have varying concentrations. They are not from standard values. They are straying from the 1 molar standard values. That means the first thing I need to find is E naught of the cell. So I will find the E naught of the cell for both of my atoms, which is zinc, and for copper. So what is the E value, the reduction potential for zinc, according to a standard table that you can find in the appendices of a chemistry manual or text? This E naught of the cell for zinc is actually negative 0.76 volts, and for copper it is positive 0.34 volts. Alright, the trend tells us that the more positive the value, the more likely it is to be reduced, and that is the copper. If this is more likely to be reduced, the zinc is more likely to be oxidized. The oxidized half relates to the anode, and the reduction half refers to the cathode. So when E naught of the cell tells us that we need to take the E value of the cathode minus the E value of the anode, we can say that that is the E value of cathode is our copper, and anode is the zinc. So now we can plug in the respective values for copper and zinc. E naught of the cell equals the E of copper minus E of the zinc. That relates directly to cathode and anode. Alright, what are those numbers? For copper we have positive 0.34 volts minus, for zinc we have negative 0.76 volts. Again, remember, we use these values straight out of the table. We do not change the signs. If the sign should be reversed because it is an oxidation process, like this is a reduction value, and yet we can see that the anode is the oxidation, so zinc is actually being oxidized. This should be a 0.76 value, a positive 0.76. We do not change that. We'll take the negative value just as it is in the table and we'll plug it in. That sign will be reversed here in the equation. We will not reverse it. So make sure you just use those values straight out of the table. The table said negative 0.76 and negative 0.76 we will use. How will that sign be flipped? A minus minus makes it the plus. And now 0.34 volts plus 0.76 volts gives us 1.10 volts. So if we were looking for the standard value, if this was a regular problem composed of an anode containing zinc and a cathode containing copper, and this was at 1 molar concentrations, this would be our E naught of the cell. But we are not operating under E naught values. We're not operating under 1 molar. You can clearly see we've got varying concentrations. So we need to use the NERST equation, which means that this E naught value is just the first step to finding E of the cell. Not E naught, but E of the cell. Which means we'll take the E naught value we just calculated and we're going to subtract from that 0.0257 volts over N times the ln of Q, which is our oxidized over our reduced. So E naught of the cell is going to be changed to give us the E of the cell, the E under non-standard conditions. So what is E naught of the cell? We said it's 1.10 volts minus 0.0257 volts over N being the number of electrons. This was copper to copper 2 plus and magnesium to magnesium 2 plus. That N value, or the number of electrons, is 2 based on that charge, times the natural log of oxidized over reduced. What is the oxidized over the reduced? What was oxidized? double check ourselves. What was oxidized here was zinc. Concentration of zinc therefore is 0.25. That's what's going to go up here. 0.25. What was reduced? Reduced was copper. What is the copper concentration? 0.15. Alright, just to show you where that's coming from. Alright, so natural log of the ratio of 0.25 to 0.15 molar, molarities canceled. Let's start simplifying here. So the first thing I'd like to simplify is 0.25 divided by 0.15 is actually 1.67. And I'd like to go ahead and simplify 0.0257 divided by 2, and I'm going to get 0.01285. And then 1.10 volts minus the product of these two would finally give me what this E of the cell would be under these non-standard conditions according to the NERST equation. So 1.10 volts minus the product of 0.01285 times the ln of 1.67. 1285 times the product of ln of 1.67. The ln of 1.67 is 0.51. Simplify even further. 1.10 volts minus the product of 0.01285 times 0.51. This times this gives me 0.00656, and E of the cell would then be 1.10 volts minus 0.00656 volts, and that gives us a grand total of 1.093 volts. So if we were under standard conditions, this would have been our voltage, our cell potential. But since we were not under standard conditions, we weren't at 1 molar, that 1.10 changed a little bit. By what factor did we change it? 0.00656. Not a lot, but still enough to render a new value. This is the correct cell potential under non-standard conditions. 1.093 would be the correct value to report.